welcome to chapter number 1, video number 2 in the 3-phase induction machine course. In this video, we are going to cover the rotating speed and field nature. So in the previous video, we covered this question. How is a rotating magnetic field produced? If a balanced 3-phase supply with frequency Fs applied to a symmetrical 3-phase winding, a rotating magnetic field of constant magnitude and running with synchronous speed will be produced. So we answered these 3 questions, but still we didn't answer the last question. What is the synchronous speed? So one of the targets of this video to know what is the synchronous speed. To answer this question, we're going to start by a 2-pole machine. We know this figure from the previous video, so we consider that one north pole, that one is the south pole, so that one is north, that one is south. So that one starts from 0 up to 360 degrees in the space, which is 0 to 2 pi, and this waveform has a frequency Fs in hertz or cycle per second. So how to convert the units from cycle per second to revolution per minute or RPM? So we are going to select this symbol NS equal 60 Fs. So if you multiply 60 by Fs, so that one give you revolution per minute rather than cycle per second. So we have the speed now in RPM equals 60 Fs. But what will be the case if we have 4-pole machine? So we have north, south, north, south. So north, south, north, south. We have in complete 360 degrees, 2 cycles. So that one will be complete 2 cycles, each of which has a frequency Fs. So to convert that one to a unit RPM, so NS will be 60 Fs over the number of cycles over one complete 360 degrees. So 60 Fs over 2. What's 2 represents? So that one is a pair of poles, right? So we can rewrite this equation as 60 Fs over P over 2. P is the number of poles, we know that one. So here in this problem, P equals 4. So 4 over 2 give you 2. So the equation now, NS equals 60 Fs over P over 2. So let us rearrange this equation. So the synchronous speed will be NS in the units of revolution per minute, 120 Fs over P, where Fs is a supply frequency. So that one is a supply frequency, and that one is the number of poles. We wrote that one before. So 120 Fs over P is a very important equation, and that one is the speed of the rotating field. Another question we need to answer: what is the field nature? We're going to answer this question using graphical method and analytical method. For graphical method using phasor form, I need to mention that this software is not designed by me, but the reference you are going to find in the bottom of the slide. But I found this one is the best way to explain how the rotating field is produced from the 3-phase. So let's look for that one. We have phase A, phase B, and phase C. They are wound in the same magnetic circuit. And we explained before how to construct 3-phase winding. So let's focus on phase A alone. So the red arrow now is going to increase up to a maximum point and then decrease up to 0 point, and then increase on the other side to a maximum point. And we explained that one at the starting of this chapter. That's, for example, phase A, that's increase up to this point and then decrease up to 0 point and then increase on the other side. The same for phase B and C, but they are shifted 120 degrees from A with respect to B, and C is shifted from B 120 degrees or 240 from A. Let's look for phase B, so increasing and decreasing at the same position. And phase C is increasing and decreasing at the same position. So each phase behaves like a pulsating field. When we're going to combine them together in the same magnetic circuit, we have a rotating field which has the equation F maximum sine omega t plus or minus theta. So F maximum here will be 3 over 2, as you can see here, that 1.5. So 1.5 equal 3 over 2, and 3 because we have 3-phase. But the nice thing that here you can find that the field has a circular nature. So the field is rotating like a circle. At any instant, we're going to add A current, B current, C current, give you a rotating field by a certain speed. This speed is the synchronous speed. Ns equal 120 Fs over P. Looking for the wave space distribution, that's the red one is the phase A, the green one is the phase B, and the blue one is the phase C. The total or the resultant field is the black one. Look for any one of the phases, A or B or C. The maximum will be at 1 or minus 1. For example, phase A is going to increase up to this point, which is positive 1, and decrease up to 0 point, and then increasing the other side up to minus 1. So these are the limits for any of the phases. But the resultant is 1.5 and moving by certain speed. So if we reverse the phases B and C, so this waveform, the black one, can move to the other side. So we can write this equation F maximum sine omega t plus or minus theta. It depends on the phases distribution. So now we have that one is moving in this direction by a certain speed, which is a synchronous speed, right? But each one or each phase, A, B, or C, increase or decrease in its position is pulsating nature, while the resultant is rotating nature. What about the analytical method? Assume we have three phase currents with magnitude I maximum and they are shifted in time by 120 degrees. And we need to calculate the MMF for each phase at certain instant time. So we are going to make a projection with respect to the angle theta. So FA of theta will be NIA cosine theta. FB of theta equal NIB cosine theta minus 120. FC equal NIC cosine theta plus 120. We're going to substitute by the currents here to have FA function of theta and time t. So that one will be NI maximum sine omega t cosine theta, and the same for B and C. If we add them together, we have the resultant field at this instant of time. So the resultant will be FA of theta plus FB of theta plus FC of theta. And the total will be N as a common factor, I maximum sine omega t cosine theta, sine omega t minus 120, cosine theta minus 120, sine omega t plus 120, cosine theta plus 120. We need to simplify this expression. So we are going to use the trigonometric identities. We know that sine x plus y equals sine x cosine y plus cosine x sine y. And sine x minus y equals sine x cosine y minus cosine x sine y. So we can write this equation. Sine x cosine y equal half. If we add these two equations together, half sine x plus y plus sine x minus y. If we assume omega t is x and theta is y, we can rearrange the equation and simplify this equation to half ni maximum, and that one is a common factor, sine omega t minus theta plus sine omega t plus theta. And for the second part here, we have sine omega t minus theta, sine omega t plus theta minus 120. And for the third part here, sine omega t minus theta, sine omega t plus theta plus 120. Well, I need from you now to look for these equation or these expressions. We add them together, they are balanced, so that one end up by 0. But we have 3 from this expression, so the resultant field, function of theta and time t, will be 3 over 2, 3 because we have 3 phase, 3 over 2, ni maximum, sine omega t minus theta. So we have a rotating field running by a synchronous speed or function of the supply frequency, omega equals 2 by f. And the magnitude will be 1.5 times the magnitude of the field for any of the phases. So that one will be 1.5 times ni maximum. Right, so now analytical solution confirm what we had before. So the function now is f maximum sine omega t minus theta. We can make it omega t plus theta, but that one it depends how you are going to select the 3-phase currents. Still, we need to confirm the rotating field nature using the analytical solution. So if we have this phasor diagram, that's IA, IB, IC. To simplify that problem, we are going to make theta equal 0 and make a projection in both x and y direction. So let's start by x direction. So for x direction, we have IA, IB, IC, as we can see here in this phasor diagram. So using equation that's fx of theta and t equals ni maximum sine omega t cosine 0, and then sine omega t minus 120 cosine minus 120, sine omega t plus 120 cosine minus 240. If we simplify this equation, so we are going to end up by fx of theta and t equal 3 over 2 ni maximum sine omega t. We're going to repeat the same for y direction, but make a projection to the y direction. So ni maximum sine omega t cosine 90, and that one sine omega t minus 120 cosine 150, and for the c will be sine omega t plus 120 cosine 330. If you simplify this equation, so fy of theta and t equal 3 over 2 ni maximum cosine omega t. If you plot this equation in both x and y, you end up by a circular field with amplitude 3 over 2 ni maximum. So the nature of the rotating field is circular with amplitude 3 over 2 ni maximum. And we proved that one before using graphical method. And we proved that one finding the function of the field using analytical method. As a summary for this chapter, we looked for the conditions of the three-phase rotating magnetic field. They are balanced supply voltage, symmetrical three-phase winding with the conditions of constructing three-phase winding. We have the synchronous speed, or this field is rotating by the synchronous speed where ns equal 120 fs over p. Fs is a supply frequency, p is the number of poles. The rotating field has the form f of theta and t equals f maximum sine omega t plus or minus theta, where f maximum equal 1.5 times the mmf for any of the phases. We proved the rotating field has a circular nature using graphical technique and analytical technique. What will I watch next? Chapter number 2, three-phase induction motor, construction, theory of operation, and equivalent circuit. See you in the next video, in the next chapter.